In this video, we will discuss several case studies of real-world convolutional neural networks. Most of these convolutional neural networks that we will discuss here are winners of the ImageNet competition in recent years. These particular architectures were chosen because they illustrate several important design principles of convolutional neural networks. We will also discuss several application-specific issues of how one might go about using convolutional neural networks in real-world applications. The first prominent convolutional neural network architecture which won the ImageNet contest was AlexNet. AlexNet brought great attention to the area of deep learning, and it featured a number of innovations that were subsequently adopted in many of the future architectures. First of all, it made extensive use of the ReLU in the convolutional neural network, which was not common before that time. Second, it also showed how dropout could be very effective. So dropout was used with a probability of 0.5. Another important characteristic of this architecture was that the MaxPooling did not use pools that were non-overlapping. It used 3x3 pools at a stride of 2, which meant that there was some overlaps among the pools. A heavy level of data augmentation was used. Here I have shown two pictorial descriptions of the AlexNet architecture. The bottom description is from the original AlexNet paper. Now this bottom description divides the feature maps into two GPUs, whereas the top description just shows an almost equivalent diagram with the use of a single GPU. And the reason why the AlexNet was partitioned into two GPUs was because in the original case, the amount of resource requirement of AlexNet was too large to fit within a single GPU. So two GPUs were used. So here, I have shown that in each layer, for example, you can see in the first hidden layer, which is C1, there are 96 feature maps. But if you look at the bottom diagram, there are 48 feature maps. That's because the 96 feature maps are divided equally among the two GPUs. Similarly, you see the dotted dotted connections across the GPU. So from layer to layer, between pairs of layers, often there are dotted connections between the GPUs. However, you can see that between some pairs of layers, we don't have these dotted connections. So that is why the bottom diagram actually has somewhat fewer connections than the top diagram. They are almost equivalent. The top diagram and the bottom diagram are almost equivalent, but they are not exactly equivalent. So as you can see, the first layer uses 11 cross 11 convolutions at a stride of 4. After that, obviously that reduces the spatial footprint very significantly, because you start off with 224 cross 224 cross 3 images and suddenly you get spatial footprints of only 55 cross 55. However, since 96 filters are used in the very first set of convolutions, you get a depth of 96. Then a second set of convolutions, you can see now you're using 5 cross 5 convolutions, but you're also combining it with MaxPooling. And because you're using MaxPooling, the spatial size of layer again reduces drastically to 27 cross 27. So the MaxPooling I've shown as MP in the top diagram. So wherever there's MaxPooling, you can see that there is a drastic reduction in the size of spatial footprint. The last, so you can see that there are these fully connected layers which I have annotated as FC6 and FC7. These contain 4096 units. Of course, in the GPU based version, they are divided into two parts. So they show 2048 units each. And the final layer, that's your softmax output, that contains 1000 outputs. That essentially corresponds to the 1000 categories of ImageNet. Now, this AlexNet, it popularized the notion of FC7 features. So you can see that in this diagram, there is this fully connected layer at the end called FC7. Now, these features, they are often extracted and they are used for applications beyond classification. And even today, when we extract these features from other architectures, which do not necessarily contain the same number of layers, they are still referred to as FC7 features, because this annotation of the FC7 features is inherited from AlexNet. Then pre-trained versions of AlexNet are available in most deep learning frameworks. So for example, if you look at any of the off-the-shelf frameworks available like Keras, you can get pre-trained versions of AlexNet. So you don't necessarily have to run the training again. You can actually use the pre-trained versions of AlexNet, extract these features, the FC7 features, and use them for a variety of applications. For example, for image retrieval. So you can, for each image, you can represent it in the form of the FC7 features and use them for retrieval or other types of applications, because these features have semantic significance. And one generally does much better with these features as compared to the raw pixels, because the features, they capture semantic characteristics of the image. As we discussed in earlier lectures, because the hierarchical feature engineering process, these features correspond to meaningful characteristics of the underlying images. Now, this signal network had a top 5 error rate of 18.2%, and an ensemble of 7 convolutional neural networks reduced the top 5 error rate to 15.4%. And this was essentially the winner of the ImageNet competition. Then in 2013, another architecture called Clarify. So Clarify was a company founded by one of the authors of an architecture called ZFNet. Now Clarify was not exactly the same as ZFNet. It was an enhancement of ZFNet, and precise details of these enhancements are not available in the open literature. Nevertheless, since Clarify, which was the winning architecture of 2013, was based on ZFNet, I will discuss ZFNet here, for which published results are available. ZFNet was very closely based on AlexNet. So in fact, I have shown the AlexNet as well as ZFNet, a comparison between the two in this table over here. So you can see there are a small number of differences. So for example, in the first layer, AlexNet performs 11 cross 11 convolutions at a stride of 4, whereas ZFNet performs 7 cross 7 convolutions at a stride of 2, but it also performs MaxPooling. So in both cases, you get the same size of layer. You get 55 cross 96 volumes. Now, in the case of AlexNet, you did 5 cross 5 convolution with MaxPooling, whereas in ZFNet, you do 5 cross 5 convolution stride of 2 and MaxPooling. So obviously, in the case of ZFNet, because you're using a stride of 2, it reduces the spatial footprint more than in AlexNet. So you can see the layer size is 13 cross 256, whereas in AlexNet is 27 cross 256. Of course, this is compensated by an additional MaxPooling in AlexNet in that layer, which is not performed in ZFNet. So again, in the next layer, you get the same spatial footprint. However, the number of filters vary. So you can see that in the last 3 spatial layers, you have 384, 384 and 256 filters in AlexNet, whereas in ZFNet, you have 512, 1024 and 512 depths. So in that tends to increase the capacity of ZFNet, because you have these larger number of filters. It can capture more number of features. The fully connected layers, they contain the same number of units, and of course, since the softmax is based on the same number of classes, it also contains 1000 outputs. Now, AlexNet had an accuracy of 14.8%, which was reduced by further enhancements in Clarify to 11.1%, and this was the winner of the 2013 ImageNet contest. In 2014, one of the prominent entries was VGG. Now, this was one of the top entries in 2014. The winner was Goulet, which we'll discuss later in this lecture. But we'll still discuss VGG because it is notable for many of its design principles which were incorporated in later architectures. So one very interesting innovation of VGGNet is that it experimented with using very small filter sizes. So filter sizes are generally odd, and in that sense, unless you are using 1x1 convolutions, which has a very different type of application, the smallest possible filter size you can use, which is odd, is 3x3. So it used the smallest possible spatial footprints of a filter of 3x3 and a padding of 1. So when you use 3x3 and a padding of 1, it will maintain the spatial footprint of the input volume. And the MaxPooling was done using 2x2 regions at a stride of 2. So in this case, we are doing non-overlapping pooling. And VGGNet experimented with a variety of configurations between 11 and 19 layers. Now, why is reduced filter size helpful? So, one point to look at it is that to look at the receptive field of a filter. So, when you have a 7x7 filter that has a receptive field, that means that in the input image, it captures the characteristic of a pixel region of size 7x7. However, if you have a 7x7 filter, that for one channel you will have 49 parameters. Now, if you look at 3x3 filters, you will have to have three layers of 3x3 filters in order to get the same receptive field, because the receptive field will increase from layer to layer. However, in this case, each layer, for each channel, you have only 9 parameters. Since there are 3 layers, you will have 27 parameters. So it reduces the number of parameters you use. Also, because the 3 successive filters will be able to capture more complex features, because it's passing through more number of non-linearities. So this principle was used in order to develop a number of different configurations. So here I show 6 different configurations here with a varying number of layers. So you can see and now I have shown the number of layers in the very first column on the top, and they vary between 11 and 19. Now, here I have shown in annotation, like when I say C3D64, D talks about the depth and C talks about the spatial footprint of the convolution. That is a 3x3 filter, depth 64. And M refers to the MaxPooling operation. So you can see that you have these, most of the convolutions are 3x3, use 3x3 spatial filters. And after every MaxPooling operation, you can see that the depth doubles, and that is not that is not a coincidence, because essentially you are compensating for reduced spatial size with increased depth, because now you can afford to spend more memory because you have reduced the spatial footprint. Now you can spend more memory on depth. Now, you can see there are also some 1x1 convolutions in some of these architectures, and also local response normalization is used. Now, local response normalization is not common in modern architecture. In fact, it was started in ResNet, but later on it was found that it doesn't help much, so it was dropped in later architecture. Nevertheless, it is described in the book. And the fully connected layers, they were similar across all the architectures, and you had an output containing 1000 units with softmax activation. And now the MaxPooling, so you can see that the convolutions, they always maintain the size of the spatial footprint, because you use 3x3 filters with a padding of 1, which maintains the spatial footprint. So the spatial footprints are always reduced by these MaxPooling layers, these M's that you see in these slides over here. And the number of filters often increased by 2 after each MaxPooling. Now, the volume, the idea was not to change the volume too much. Well, it doesn't exactly remain constant, because the spatial footprints are increasing along both dimensions, whereas the depth is only increasing along one dimension. But the idea really here is that you want to increase the depth while you reduce the spatial footprint. Now the VGG had a top 5 error rate of 7.3%, and column D was the best performing architecture, the 16 layer architecture described in the slide. Now, in the same year, GoogleNet was proposed, which is a play on the word LayNet, which was the very first neural network architecture proposed by Jan LeCun. Now, the initial part of the architecture is much like a traditional convolutional neural network and is referred to as a stem. And a very key part of the network is an intermediate layer referred to as an Inception module. And the idea in the Inception module is that it allows us to capture features of images at varying levels of detail in different portions of the network. So the idea here is that for any given image, different types of features in different parts of the image may be best captured at different levels of granularity. And by allowing a large filter, so a large filter can capture information in a bigger region containing limited variation, whereas small filter can capture detailed information in a smaller area. And piping together many small filters is sometimes wasteful if in a particular region of the image you have a relatively simple feature. So you want the neural network to have this ability to decide how much to capture in what region of the image. And this is done by using the Inception architecture, where you have this kind of parallel pipeline where you are using convolutions of different size. So you have these 1x1 convolutions, 3x3 convolutions, 5x5 convolutions, and also you are using MaxPooling. And then you're whatever you're getting out of this, you're concatenating the filters. So in a sense, you're creating different feature maps at different levels of granularity. And one problem with this approach is computational efficiency. And note that this module, you will create the whole neural network architecture by putting together many of these modules. But the problem with these modules is that if each of these modules is inefficient, it makes the process of training quite inefficient. So one way in which this problem was solved was by first reducing the depth. In order to reduce the depth, what was done is that 1x1 convolutions were used. Now note that 1x1 convolutions don't change your spatial footprint. But for example, if you have a depth of 256, you can use 1x1 convolutions. You can use 64 filters and 1x1 convolution to reduce your depth to 64, and then you can perform the same operations that you had in the previous slide on these reduced depths. So this is essentially an efficient variation of the Inception module. Now, another important design principle was the innovations in the output layer. Now, it is common to use fully connected layers near the output. So, for example, in all the earlier architectures, every neuron is connected to every neuron in the fully connected layer. Every neuron in the spatial volume is connected to every neuron in the first fully connected layer. However, GoogleNet, what it does is that it uses average pooling across the whole spatial area of the final activator to create a single value. So what will happen is the number of features created in the final layer will be exactly equal to the number of filters. So whatever the number of filters in the final layer, that will be equal to the number of features in the first fully connected layer. And this helps in reducing the parameter footprint. In fact, the largest consumption of parameters in many of these convolutional neural networks happens in the fully connected layers. And just this simple change greatly helps in reducing the parameter footprint. And one of the principles behind this is that detailed connectivity is not required for applications in which only a class label needs to be predicted. So here I have shown the architecture of GoogleNet. So you can see that you have these Inception modules, these little modules in the middle. You can see they have a very similar shape to the module that I showed here. So you can see that you have these sets of Inception modules which are hooked together to create the full architecture. Now, GoogleNet was the winner of ILS VRC 2014, and it reached a top 5 error rate of 6.7%. Note that this is better than VGG. It contained 22 layers, and several advanced variants were proposed with improved accuracy. And some have been combined with a recent article called ResNet, which is what we'll discuss in the next slide. Now, the motivation for ResNet was the difficulty in training with increased depth. So, it was clearly shown in the increased performance on the ImageNet competition in successive years that as you increase the depth, one tended to do better and better. However, the problem is that it also made the network harder to train. So, you couldn't possibly increase the depth beyond a certain point. And in these cases, what happened is that even the error on the training data was high. So you would think that if you have a network with large enough capacity, at least on your training data, you should be able to overfit enough that at least on the training data, you get very low error. But if even your error on the training data is high, what it means that there's very poor convergence. What it means is that gradient flows across the layers are impeded. So selecting an architecture with unimpeded gradient flows is helpful. So and ResNet made a number of changes to the convolutional neural network which brought the depth of neural network into the hundreds. And it was based on the principle of iterative feature engineering rather than hierarchical feature engineering. And the principle was to partially copy the features across layers. And we have actually heard this before in several architectures that we discussed before in the case of recurrent neural networks. So recall that the LSTMs and the GRUs, they use gates to partially copy features from layer to layer. Well, in the case of ResNet, the gates are fully open. And just the change made the performance of ResNet very close to human level performance with a top 5 error rate of only 3.6%. So here we discussed the concept of skip connections. So in skip connections, what we are doing is that we are allowing the copying of the features between two layers. So you can see that there's a skip here. If you look at the residual module, you're allowing a copying, so it has an option of either going through the operation, either going through the weight layers or just skipping over the layers. And you can put many of these residual modules together to create as long an architecture as you want. So that is shown on the right. So as you can see, these skip connections, it can keep skipping one after the other, and it can straight from the input to the output, it can actually go through very few layers to get to the output. So the idea really here is that it's going to use whatever level of nonlinearity and processing is required to capture the complexity of a particular part of the image. Now note that even in the case of the Goulet, we achieved this type of idea using a different principle of an inception module. Here we are doing it with the use of skip connections. And the idea here is that you don't really need a lot of layers to capture some of the simpler features in the image. So for those cases, it can, for those portions of the image, for those features that can be captured with a smaller number of layers, you give these skip connections to enable the learning of those features. And then the residual portions of the image are learned with a larger number of layers. That is why this is called ResNet. That is why the concept of residual learning is so important in this case. So here clearly you can see that there's an iterative feature engineering. Whatever you can learn with fewer layers, you learn with fewer layers, and then the more complicated thing that you cannot learn with fewer layers, you iteratively learn with more number of layers. Now, some of the details, it used a 3x3 filter at a stride or padding of 1. This was adopted from VGG and it maintains the dimensionality. And some layers use strided convolutions to reduce each spatial dimension by a factor of 2. A linear projection matrix reduces the dimensionality. So the projection matrix defines a set of 1x1 convolutions with a stride of 2. Now, why do you need to reduce the dimensionality? Note that in some of these layers you use MaxPooling. So when you use MaxPooling, the size of your spatial footprint is going to reduce. So you can see that in some cases these skip connections are dotted, and they are dotted wherever there is this reduction in the size of the spatial footprint, because in those cases the skip connection will really need to use a 1x1 strided convolution, a 1x1 convolution at a stride of 2 to reduce the spatial footprint. Now you can clearly see that there is an improvement from year to year, and this improvement mirrors the increase in the number of layers. Now one point I think I neglected to mention, all these errors that I've been quoting, they are top 5 errors. So top 5 error essentially means that the top 5 results that are reported, the top 5 classes that are reported, the correct class is one of these top 5. So you can see the top 5 error reduced from year to year, and corresponding the number of layers also increased from year to year. ResNet in particular is very impressive. It has 152 layers, but there are many variations of ResNet which have even larger number of layers. Now, many of the models discussed in the previous slides, they are available as pre-trained model with ImageNet data. And one can use the features from fully connected layers for nearest neighbor search. So you can use it for all kinds of other applications. You can use it for search, you can use it for clustering. You can also train the output layer for other applications like regression while retaining the weights in other layers. So what you can do is that you can download one of these pre-trained networks from Keras, and then you can hold all the weights fixed and just train the output layers. So essentially the features for your images are being learned using your pre-trained model right up to the final fully connected layer, or you can even learn the fully connected layers. So you don't need to train any of the spatial layers, you can just learn the fully connected layers and the output layer, just the weights of the last few layers, or even if you want only the output layer. Now let's look at a particular application like object localization. So in image recognition, we just wanted to classify an image. So if you have a fish, you would just want to classify it as a fish. In object localization, you want to classify image together with its bounding box. So here you will have 4 numbers corresponding to the bounding box of the image. So for example, you can have the top left corner as well as the width and the depth, width and the length of the image. So here what you can do is that you can take the pre-trained model. You don't really need to retrain it for the whole object localization problem. So you could, for example, first train your convolutional network using ImageNet as if it's a classification problem. Then what you can do, all the convolution layers, you can hold their weights fixed as if you have learned them. And now you can train it with your object localization data. So it's assumed that you have training images with these class levels as well as these 4 numbers given to you. And what you do is that you attach 2 heads, so you change the output layer. So you have a classification head and you have a regression head. You attach both to these convolution layers. So you can train, you have 2 options. Either you can train the classification heads and the regression heads separately, or you can even train them together with your training images. In fact, it's better to train them together. And this has been used for other applications. So for example, when you have object detection, you might have multiple objects rather than a single objects. It has also been used for text and sequence centric applications. Convolutional neural networks can be used for text by using one-dimensional convolution. So text can be viewed, since text is a one-dimensional sequence, rather than looking at the spatial footprint, you are looking at the one-dimensional sequence, and you can use one-dimensional convolutions. It has also been used for video and spatiotemporal data with the use of 3-dimensional convolution. So you'll have 3-dimensional filters along with a depth. So all of these applications, they are discussed in some detail in the book.